Science Museum of Minnesota, and welcome to our show, Cryogenics, the world of ultra cold temperatures. So low that if I take this piece of stretchy, everyone can see, we'll take a couple of pieces of stretchy rubber and put them into this ultra cold liquid for, oh, I don't know, let's just say 1, 2, 3 seconds. Their properties have changed dramatically. But how cold, that's not supposed to be in there, how cold is cold? Well, for that, we're going to go ahead and take a look at our temperature scale, or otherwise known as a thermometer. And the scale we're going to be talking about is Fahrenheit, which is one everyone's probably most familiar with. And we're going to start way up here at 212 degrees Fahrenheit. Who can tell me what hour? Shout out if you know what happens to water at 212 degrees Fahrenheit. It boils, absolutely. And above that temperature, water is a gas. Below that temperature, water is a liquid. Now we're going to cruise all the way down to 72 degrees Fahrenheit. And I want everyone to put their arms out like this and say, yeah, that's nice, right? That's the temperature we keep the Science Museum of Minnesota at. That is a really super awesome temperature in the summer and the winter. This is the best place to be. We're going to go down to 32 degrees Fahrenheit. Who knows what happens to water at 32 degrees Fahrenheit? Shout it out.
It freezes.
It freezes, that's right. And above that temperature, water is a liquid. Below that temperature, water becomes a solid. Now, to some people in other parts of the country, 32 degrees is a really cold day, right? Not to us here in Minnesota. In February and January, that's a really warm day, right?
Yeah.
We're going to cruise to 30 degrees below zero. That is a cold day here in Minnesota, and even that's warm some days.
Roxanne.
We're going to go down even further to 109 degrees below zero. That is the temperature of dry ice. We're going to go down even further. We're going to go down to 129 degrees below zero. Ooh, that is the coldest temperature ever recorded on Earth. Does anybody know where that was?
Where we are.
Antarctica, that's right.
Call us and tell us about this.
Even further than that to 320 degrees below zero.
You'll hear my phone go off.
That is the temperature at which nitrogen gas condenses into a liquid. That is an ultra cold temperature so
Kesha's going to start singing
that it can cause instant frostbite. So, before we go any further, I do want to make sure that we go over a safety thing. For those of you sitting on the sides, that's totally cool. For those of you sitting in the front row, the main thing is if anything falls onto the floor, please do not touch it. I am going to be pouring some liquid nitrogen onto the floor. There is a possibility of some ultra cold things falling, which can cause frostbites. If anything does fall there, just do not touch it. If we have a deal, let me hear you say deal.
Valid.
Excellent, let's get started. Sweet. So, 320 degrees below zero is the temperature at which liquid or nitrogen gas condenses into a liquid. And this is what you get. You have this awesome, really cold,
it's bubbly,
ultra cold liquid. And we'll raise this up and be a little bit more reckless with it so that everyone can see how cool this stuff is. All right. So as you can see, what does it look like our liquid nitrogen is doing? Shout it out.
bubbly.
It looks like it's bubbling or boiling, right? Now normally to make something boil, we need to add heat to it. Are we adding heat to this liquid nitrogen?
No.
Yes, absolutely. Remember, this is 320 degrees below zero. How warm is it in here? 72 degrees, right? That's nearly 400 degrees warmer. So this room is acting like a big oven for this liquid nitrogen. And I'll show you, this floor is also about 400 degrees warmer. And if you can see, there are tiny little droplets. For those of you in the front row, yeah, they look like water on a hot pan, right? And this table is also about 400 degrees warmer. So you'll notice, though, I pour it, right, and it kind of disappears, right? It starts to turn back, it starts to evaporate and turn right back into a gas pretty easily. Now, is this nitrogen gas that we're seeing when I blow here? No, it's actually not. Something you should know is that nitrogen makes up 72% of the air we breathe. So if you could see nitrogen, it'd be really annoying. You guys wouldn't be able to see me, I wouldn't be able to see you. That's cold. What you're actually seeing is water vapor. The ultra cold temperature of the liquid nitrogen is condensing the water molecules on my breath, and you're seeing vapor. But there is a couple of ways that we can tell that the liquid nitrogen is turning back into a gas. Do I have any tea drinkers in the audience? Raise your hands. All right, lots of tea drinkers. Any hot cocoa drinkers? Yeah? Oh, there we go. Everyone likes at least hot cocoa. What is the sound the tea kettle makes when it's boiling and ready? All right, it whistles, exactly. And that's how we know it's ready. And remember that above boiling point, that liquid is turning into a gas. So let us see what happens when we put liquid nitrogen into our tea kettle. We're ready. Anybody care for a glass of ultra cold liquid nitrogen? No, of course, no, that would be very, very bad for you. So the liquid nitrogen is essentially boiling, and it's turning back into a gas and has nowhere to go except through the whistle of our teapot. There's another way that we can see that liquid nitrogen is turning back into a gas. And for that experiment, we're going to go ahead and take one quick second and think like scientists. When scientists do experiments, they observe the world around them using their senses. So we're going to use our senses and describe this rubber hose. What color is it? Black. And what do we have at the end? We got a glass.
Needle.
Glass tube and a cork. And would you guys say it's bendy or stiff?
Bendy.
Okay, so we've got a black, bendy rubber hose. Remember all that, okay? And we're going to go ahead and put a little liquid nitrogen in this flask. And this right here, ladies and gentlemen, if you have not taken chemistry, take this down because you will be able to impress your teacher and say, well, professor, is that not an Erlenmeyer flask? That is the technical term for this flask. If you want to see really, really with it. All right, and yeah, we're good. That's all right, cool. So we got liquid nitrogen in our Erlenmeyer flask. We've got a black bendy rubber hose with a cork and a glass tube at the end of it. And let's go ahead and cap our Erlenmeyer flask.
It's like shooting things out.
All right, get out of there. There we go.
It's almost like fire.
Okay, it's taking a little longer than usual, but as you can see, there we go. There is gas. You can see it looks like there's smoke coming out. I think we've got a thinner tube than usual. It's not actually smoke. It's once again water vapor. The ultra cold temperature of the liquid nitrogen turning into a gas. The gas has nowhere to go except through our rubber tube, and the ultra cold temperature is condensing the water molecules in the air. And some of you might think that I'm actually moving this flask around to make the liquid nitrogen turn back into a gas and come out. That is not the case. The reason I'm moving our flask here is because if I don't move it, it will freeze to the table, which I have learned a number of times. You have to wait about 15 minutes before it unfreezes. So the liquid nitrogen is turning back into a gas, and it is slowly escaping through our rubber hose. And what color is our hose now?
Gray.
White or gray. And is it bendy or stiff?
Stiff.
All of a sudden, it is stiff. And I owe the Science Museum of Minnesota like $35 for a new black bendy rubber hose. Let's hope it goes back to normal. But the effect that this ultra cold liquid had on this rubber hose and on our piece of latex at the beginning of the show shows us the effects of ultra cold temperatures on solids, right? And the study of the effects of ultra cold temperatures is cryogenics. Now we're going to be using the coolant liquid nitrogen to see what ultra cold temperatures do to liquids, solids, and gases. So we're going to move on, and I'm going to need a volunteer from the audience.
Go Val, raise your hand.
You right there. And what is your name? Sarah? Sarah, do you know how to blow up a balloon? Would you blow this balloon up to about the size of a grapefruit, about that big, okay? Then if you can tie it off, that's awesome. If not, just hold it and I'll tie it. And I'm going to need another volunteer from the audience. How about you right here? And what is your name? What's that? Naya. Naya, do you think you can make your way over this bench? Come over here. All right, so Naya, thank you so much for coming on up here. So Naya, I've got a ball right here. I want you to discover and tell us some of the properties of this ball. It's bouncy. Can you prove that it's bouncy? It is bouncy. Nice bounce. Anything else? It's soft. Can you squish it? Yeah, it's a little squishy, right? So remember that. We've got a squishy, soft, bouncy rubber ball. So if you'd stay seated in the front row right next to this gentleman right here, I'm going to ask you for your help in just a second. All right. Looks like we have a tag team. Okay. You got it? Actually, we'll go ahead and place our rubber ball. We'll see what happens after we put it in our liquid nitrogen for a little bit. I can finish that off if you need help. You got it? That's always the most difficult.